Hello and welcome back. We're going to go over a few problems from yesterday's assignment. So if you had some issues with the front side or the back side, we're going to do some of those problems together here. So we'll start at number 6. So at this point we should already have E, Q, and C as our solutions. So we want to look at points O, L, K, and M, and we want to know if they're coplanar. So first we have to remember, what does coplanar mean? Well, we see the planar word, so it's referring to the plane, and co means the same. So we want to know, are these on the same plane? So let's look at our points over here. We have O, L, and K. So far, O, L, and K, those are all on this horizontal plane, plane X. So the only question we have now is M also on that plane? Well, it looks like to me M is going to be below that plane. So those are not going to be coplanar, so we could actually cross that one out, so that would not be true. Then we have points C, O, A, and B. Are those coplanar? All right, this is where it gets a little difficult with number 7 and number 10. So if we look at A, O, and B, those three are collinear. They're on the same line. So A, O, and B, if we had a plane that went through those three, it would be a vertical plane that's going up and down. Now, what's challenging about this is the only plane that they show you is the horizontal plane. But that doesn't mean that's the only plane that exists. In fact, we can create a plane through any three non-collinear points. We can define a unique plane that way. So what we would need to do is we need to use our imagination, like Barney or something. But we need to imagine a vertical plane. And so I went ahead and drew that out for you so you could see it. So we have a vertical plane that goes through A, O, and B. But the problem with defining this plane by A, O, and B is that it's not well defined because it's allowed to rotate. Because A, O, and B are collinear, any vertical plane would go through all three of those points, and it would still be allowed to rotate 360 degrees, if you can imagine that whole thing spinning around 360 degrees. So once we go through A, O, and B, the third point, which is C, this point over here, we could simply rotate this vertical plane until it hits C. So can you see a plane that goes through A, O, B, and C? Yes, absolutely. So there is, those four are coplanar. So that would be our second letter here, which would be L, or our fourth letter. And let's go ahead and jump down to number 10. That's a similar thing going on there. Points A, B, and M are coplanar. So you have A and B again. So we're talking about a vertical plane. But now we need point M. I'm not sure where M is, somewhere underneath the plane, but we do know with just points A and B, we could rotate that vertical plane around until it does go through this point M. Now I wish I could interact with this and just click it around and drag, but unfortunately it's not that easy. So what you might be noticing about geometry is it's very spatial, and you need to be able to imagine things moving around in space. And so this is obviously a lot easier for me to teach in person, so I understand the struggles that you guys are feeling, and I'm trying to do my best to give you good visuals. But we're going to make it through this together, okay? So don't worry. And also, some of you, I was grading your homework assignments and you were having issues on certain problems. If you'll go ahead and tell me what problems you need help on, I have a solution manual. I can just simply copy and paste some of those solutions to keep you going so that you won't get completely stuck. But if you don't ask for any help and you don't tell me what problems you would like help on, then I'm just going to assume you're getting it and you know what you're doing. I'll try grading them close as much as I can, but that'll really help. And if you like more immediate feedback and immediate help, you can always reach me on Remind. It'll go straight to my phone, so I'll get it sooner than if I just find that you message me through Google Classroom. Usually it just takes whenever I get around to grading when I'll see those, or most of them. Okay, so A, B, and M, that is going to be coplanar as well, so we are going to use the D, so I guess we could circle that if we wanted to. Let's look at plane D contains point P. So let me move this vertical plane out of the way. So we're back to what we started with. Plane D is actually going to be referring to this plane over here. It's on our second image. So just plane D, the horizontal plane, is that going to contain point P? Well, if you notice, point P is actually on the vertical plane, plane E. It's going to be below plane D. So no, it's not going to contain that. So that one's going to be false. So we can cross that one out. Actually, sorry, that would be this one right here. And then plane X intersects line AB at O. And I know this is a line because it's got arrows in both directions. So plane X, our horizontal plane, intersects line AB, which is our plane that's going, or our line that's going vertically, and it is going to pierce the plane at point O. We know it pierces and goes from above to below it because right here these dotted lines tell us that that part of the line is covered up and behind the plane that it's showing. So that's how we know that it's going above and below it. So if you can kind of imagine a flat plane, the line is going straight up or piercing through that plane, going to the top and to the bottom. Okay, so again, kind of hard to imagine. You just have to be able to look at the visual cues to be able to see what's going on with a 3D. So that is going to be true. So our next one is going to be I, and then after that would be our D. And you probably know what the spelling, it's Euclid. So the last one will be S. So if you haven't gotten there now, spoilers, it's Euclid's. All right, so on number 19, so we have Euclid's, and then ELE is the starting of the next part. Look at 19. It says points G, N, F, and P are coplanar. So again, are they on the same plane? So G, N, and F, once again, G, N, and F are all on the same line. They're collinear. So what that means is that this plane here that goes around those lines is allowed to rotate 360 degrees. So technically, any other point would be coplanar with points G, N, and F. The other point they're saying is P. So yes, those would all be on the same plane E. But keep in mind, if I tell you G, N, and F, because they're on the same line, it's still allowed to rotate 360 degrees. So it didn't matter if I said G, N, F, and H, G, N, F, and Q, G, N, F, and this point way over here, point X. We could rotate that horizontal plane until it does finally have a plane that goes through point X. Might look something along the lines of that. That is a rough sketch. You are so welcome. All right, so that one was true. Then we have Q, H, N, and F. Let me go ahead and clear that out real quick. All right, so Q, H, N, and F. So Q, H, N, and F. It looks like all of those are going to be on plane D, so those are going to be coplanar. So that is circled. So E, L, E, M, E. So next two, and then N and P are on plane D. So N and P, okay, N is on plane D, but P is actually on plane E. So that's not going to be true. So we can cross that one out. The last one is angle GNH lies on plane D. So angle GNH is going to be this angle right here. Let me change colors so you can kind of see what I'm drawing. But we start with G, then we go to N, then we go over to H. So that's referring to this angle right here. That's angle G and H. And if you notice, the entire angle is on plane D, the horizontal plane that they have drawn for us. So that one is true. So 2, I think it's still green. Yeah, that's fine. All right, so if you can't tell by now, the word we're spelling out for the solution from yesterday is Euclid's elements. So last two would be T and S. So you can work backwards from that and see what you did wrong if you're missing any letters or anything like that. Okay, so let's go ahead and get started. We're just going to do a quick review. There's nothing really too new today, just another way of thinking about segments and circles and annotating angles. Then we'll go right into the assignment for today. So I'm going to try to keep this short for you. There's nothing really too terribly new. So you got 2 days to kind of wrap your head around this with another assignment as well, okay? Then we're going to move on to segment addition, which is pretty simple. Tomorrow will be an easy day for you. All right, so segments are part of a line that has 2 endpoints. So there are actually 3 segments shown here. We have segment AB, segment BC, or segment AC, which is the whole thing there. So what I want to point out, let's say we start out with segment AB, which is the purple segment there. Even though this looks like a solid line with 2 endpoints, keep in mind that solid line is not actually a solid line. It's actually the collection of all possible collinear points that are directly in between points A and B. So all the possible points that exist between A and B, strictly between A and B, that are collinear, those are all the points that make up segment AB, okay? So I actually could draw more and drag more points over here. It's kind of cool. Anyway, so imagine just infinitely many points that exist between A and B, and they're so densely packed together that it looks like a solid line. That's really how we should be thinking with geometry, because at any given point in time, I can label one of those, a letter that we haven't used yet, like P, or this one here could be H, and this one here could be G. Usually we stay in alphabetical order when we start naming them, but as soon as we label them, we can do I for this one, they exist and they're official and they have a name, the location based on whatever letter you assign to them, okay? All right, next we have same thing if we were doing our second segment, which could be BC. So BC is the collection of all collinear points that are strictly between B and C. So now we're talking about all these points. Kind of feels like I'm playing with one of those old counting machines that they had with all the sliding things. Anyway, it's kind of fun. So now it's talking about all the collection of all collinear points that exist strictly between B and C. So infinitely many points there. Then the last one would be segment AC. So once again, all the possible points that exist strictly between A and C. And keep in mind, there's still infinitely many. Oh, that's the last one. There's infinitely many of them that exist on that. I'm using infinite a lot, aren't I? Anyway, so that's a segment. So same thing I want you to think about a circle. So a circle is a set of all equidistant points from the center. So what does this word here mean? Equidistant. So distance obviously is distance, and equa is equal. So equal distance from the center. That's actually what makes up a circle. You probably know that. And we construct circles using a compass like we have here. So let's say we want to construct circle B that has a length of the radius of segment AB. So once I set the length there, all I have to do is draw going all the way around here. That was off a little bit, so let me try it again. See if I can get it more in the center. Okay, we'll call that good. All right, so there's my circle, much better. And if you notice the setting, this distance here for the radius of the circle, it never changed. So all the points that are on that line are all going to be the exact same radius distance to the center. So again, this looks like a solid line. A circle, you probably always thought of it as like one curved solid line, but it's not. It's actually, just like a segment, the collection of all points that are equidistant from the center in this case. So we have all these points that we have here. Let me go ahead and move this to the back. There we go, so you can see the points front and center. And then keep in mind, in between any two points that you pick on the circle, there's infinitely many points that exist between those 2 points. So there are a ton, or infinitely many points, that exist that make up this circle. That's why it looks like a solid line, but it's not really a solid line. And at any given time, you can just start naming them off. So we already have points A, B, and C. So we could call this one D, we could call this one E, and then F, and then G, and this one could be I, or H, and then this one could be, I didn't do H yet, so H, and then J, and K, etc. So as soon as you name them, it's like, boom, it's there, and sure enough, hey, let's say I want to make one right here. Okay, well, it's there. It was always there, it just didn't have a name. Now I'm drawing your attention to it and giving it a name, J, K, and then L. No, I'm serious. And then this one could be M, and then over here, this one could be N. So this idea and way of thinking about geometry with these shapes and these points and locations and lines and planes, I'm just trying to get you to think in this way. So even though it's not there, it's technically still there. You just have to draw attention to it. Anyway, we'd actually annotate that as circle B. So if we had multiple circles that had the same center point, but different distances, kind of gets difficult because that would also be considered circle B because it's named off of its center point. So figure that one out. It's kind of weird. All right, so next one we have a line. So a line is a collection of all collinear points that are in between 2 endpoints and also extend in both directions. So it's a set of all collinear points between 2 endpoints and extending in both directions. So there are 3 segment or lines we could say here. We could call this line AB. That would be the one in red. We could also call it line BC. That would be the exact same line, right? Because all 3 of these points are collinear. Or we could call it line AC. So again, the blue one there. It doesn't matter which one you pick. They're all the same line. They all have the same length, which is that to say infinite. All right, planes. So I made some beautiful diagrams here. I think you'll like them. Just so you can see kind of how planes work in some intersections of planes as well. So here we have a cube, and it looks like plane we're referring to is plane ABG. So from A to B and then all the way down to G. So the other point that would be on the same plane is H over here. Okay, so if you want to draw this plane, all you do is connect the dots from A to B, B sideways to G, G to H, and then H sideways to B. And then all you would need to do on your paper, because I know you can't do all this cool graphic art, is just shade it. Just like that, and that will let me know that you know which plane you're referring to. So connect your lines, and of course they're not going to be totally straight like mine. And then draw your arrows showing that you understand that the plane, like a Cartesian plane, extends forever in all directions. So it's not just the rectangle that you would see there, it actually keeps going, and that's why this plane here kind of shows that it's keep going as well. And if you like art, you probably kind of pick this stuff up pretty easily, but these ideas, oops, that was kind of weird. The idea is that they extend forever, and how you show the front face longer than the back face, because that kind of gives depth, like a 2-point or 1-point perspective. It's pretty cool. I'm not really huge on art, but I do like doing graphic art like this. It's kind of fun for me. Here's another plane and an intersection you could have. This would be plane GD, so from B to D and then down to G. So notice this one is, the intersection is going to be a triangle here. You can kind of see how I show the plane there as well. So before we talked about planes that were on the top or the bottom, the front or the back, and the left and right, but they don't have to intersect like that. We could have diagonal ones here. We could also have ones that are even weirder in diagonal, I suppose you could say. So sky's the limit, really. Between any three non-collinear points, there exists a unique plane. It's just drawing it out is where it kind of gets a little bit confusing. All right, so a ray is a geometric figure that is part of a line with one endpoint, so it has a starting place, and then it goes forever in a single direction in a straight line. There are three rays we have here. We have the red, the green, and the blue. Which ones are opposite rays? So an opposite ray are two rays that start in the same place and they go in opposite directions, forming a straight line. So in this case, our opposite rays are going to be BA and BC. But not every two rays that start in the same place are going to form a straight line, right? Or opposite rays. We could use the blue and the green. They both start at B, but they go not in opposite directions. They just form an angle. In this case, it would be an acute angle, but that's okay. All rays that start in the same place are going to form angles. It's just if it's a straight angle, then they're opposite rays. Is kind of what's going on there. All right, opposite rays, again, start in the same point, and they go in opposite directions. So if you can kind of draw that out, start at the same point, and they go in opposite directions, just like that. It's kind of how I visually show that with my hand signals. So here we have BA and BC. So BA is going to start at B and go through the direction of A, and then BC starts at B and goes in the direction of C. Those two form line AB or line AC or line BC, doesn't matter which one you want to say. They start both at B and then go in opposite directions. So those are opposite rays. Collinear points are points that lie on the same line. That's what co means, same linear, same line points. Points on the same line. All right, so our collinear points in this case are A, B, and C. D is not collinear with those 3 points because they are not on the same line. Now, if I move D down here, now all 4 of them are collinear points, but right now, it's not on the same line. Annotating an angle, so here we have 2 rays that start in the same point, so they form an angle. They're not opposite. It's not an opposite angle or a straight angle. They're not opposite rays, sorry. So how do we annotate this angle? Well, we start with one of the endpoints, or not the endpoint here. This is actually called a vertex. Actually, I could type it out for you in case you're wondering. Vertex. We'll talk about angles more later, but might as well tell you about it while I'm here. The vertex is the common endpoint of the 2 rays, okay? And whenever we name the angle, we never start, the vertex always goes in the middle. So CAB or angle BAC. Notice how in the middle is the A. So we could either call this CAB or you call it angle BAC. Doesn't matter the order, these two are equivalent. It's the same thing. It's like saying segment AB and segment BA. Those would be the same segment, but with rays, that's not the same thing, by the way. All right, so some names for angle 1. We could call it angle CBF or angle FBC. So that's the first one. For angle 2, ABC or angle CBA. Doesn't matter which order you do, as long as the common endpoint, the vertex, is going to be the middle one. So BB. So we're good to go. All right, so if you get out your assignment, so that was the lecture. I think the lecture was like 10 minutes of review, and then we did about 8 minutes for the assignment problems from yesterday. So trying to speed it up a little bit for you. Let's look at number 14. The first problems 1 through 11, you should be pretty good, especially 1 through 8. So you also got your answer bank there. There was a typo on the answer bank, I think, for 31 yesterday, and it was a problem that I did with you, and it wasn't on the answer bank. So besides that, I think the answer banks were good yesterday. All right, shade the plane that contains the given points. We have E, H, and B. So E and H, and then B. So obviously that's going to be this diagonal one here. So whenever you're going to shade that on your end, all you have to do is connect from E all the way up to B. And you can draw your line going straight across, and then your line going down. That was terrible. Alrighty, we'll just do the whole thing again. So going straight across, going here, and go in here. It doesn't have to be perfect. You can take your time if you really like art, and then just shade it in by just drawing your squiggly lines there, and then let me know that you know that it's a plane that extends forever in all directions, just like the Cartesian plane. And that's it. Number 15, this one's a little bit more difficult. It's kind of hard to draw. I make it look easy, but I can do digital art. It takes me a while. So we have A, C, and E going from point A to point C and then down to, I said E, but that's actually H. So you can connect your lines. So going straight across from A to C, C all the way down to H, and then H all the way over to A. And then you can just scribble that in right there and then draw your arrows showing that that it goes forever in all those directions. That might be how you would visualize what plane we're actually referring to, but you don't have to draw the outside. If you want to try it, you can. So just make it longer, on the front side. Let me see if I can. Yeah, so just make it longer on the front than you do on the back side. That'll give it its depth and perspective if you're liking art. All right, 16 through 20, determine whether statements always, sometimes, or never true. Understand these problems are hard, but I want you to really think through them and see if you can get them with the answer banks, okay? So number 16 says, ray GH and HG. Now, how do I know those are talking about rays? Look at the symbol. It's got an arrow going in one direction, so it's ray. So ray GH and ray HG are the same ray. Is that true? Can that ever be true? We'll think about it. You can even draw it out if you want to help. So if we do ray GH, starts at G, goes in the direction of H, it's going that way, and then ray HG starts at H and goes through the direction of G. So they're going in, well, clearly in opposite directions, right? They're not opposite rays because they don't start in the same place. But are they the same ray? No. We know they're not the same ray because they don't start in the same spot. So if these were segments instead of rays, so if this had an endpoint here and this one also had an endpoint, then you could say that they are the same segment. I don't know if I can click here. Because segment GH and segment HG are exactly the same segment because they have the same endpoints. The collection of all points between G and H and G is exactly the same. But when we're talking about rays, now they're different because they're starting in different places, so they're going in opposite directions. So that one would be never true. So you can just label it in if you want. I understand you guys are lazy, me too. I don't want to write out never. And then we can cross it out on the answer bank as we go. So what about ray JI and JL? Are they opposite rays? Well, they do both start in the same place. They both start at J, so it's got something going for it. But does it have to necessarily be opposite rays? Well, just from the description JI and JL, unless I knew that I, J, and L were collinear, then I would know. But I don't know if I, J, and L are on the same line. So right now, JI and JL are opposite rays. But what if I is actually up here? Now are they opposite rays? No, because they're not going in the same. So if all three of them were collinear, then I would have enough information to know that they would be opposite rays. But if they're not collinear or non-collinear, then they form an angle instead of a straight angle and opposite rays, okay? So that is sometimes true. So it just depends if they're collinear or not. So that would be one that's sometimes. All right, 3 points are collinear, which means they're on the same line. So if we have 3 points, do they have to be on the same line? Well, it's kind of related to the last one. 3 points can be collinear, but they also could form a unique plane like this one does. So it just depends. So that would be sometimes true. So I don't know what the last two are going to be. Probably should have rearranged the order of those two, but that's okay. See if you can make sense in your head of why the last two have to be always true. And that's it. So right under 24 minutes. So don't really have anything else to say except if you're struggling, make sure that you ask for help. Otherwise, because I've got a whole set of solution manuals that I already have them all typed up in Google, in a Word doc, and all I have to do is copy and paste those solutions to you for whatever problems you need help on. So it's no problem to me. It's my job. I want to help, but if you don't ask for help, you're just struggling on your own. So don't do that. And if you need my help for a technical issue or something you really want to get my attention quicker, you can always try getting my attention through Remind, because that goes straight to my phone. So I hope you guys have a good day. I hope you're not stressing out over all this stuff. Of course, I wish I could see you guys in person, and I wish I could teach you this in person. It's a lot easier to explain planes and three-dimensional stuff, but I'm trying to do my best with the graphics and kind of enjoying making those things anyway, and the videos. But I hope you guys have a good day, and I will see you guys tomorrow.